Hello my friends and welcome back to the You Can Do TV channel. Welcome to the Kubal Aluminium Smelter, the sole aluminium smelter in Sweden, where approximately 130,000 tons of aluminium are produced annually. Today, we will explore both the smelting and casting processes, starting with an introduction to the raw materials involved. Raw materials. The primary raw material for aluminium production is alumina, aluminium oxide, which is a white powder. This alumina is derived from bauxite, a mineral containing about 50% alumina. Bauxite is processed into alumina elsewhere before it arrives at the smelter. In the smelting process, alumina is dissolved in a molten bath consisting of cryolite at a temperature of approximately 900 degrees Celsius. The smelting process. Electrolysis is the core method used to convert alumina into aluminium metal. The electrolysis occurs in the pot room where large cells, or pots, contain the molten cryolite bath and alumina. The electric current passes through the bath via anodes, carbon blocks, and cathodes, bus bars. Anodes and cathodes. The anodes are consumed during the process, needing replacement approximately every 30 days. The electric current flows through these anodes, causing the alumina to break down into aluminium metal, which settles at the bottom of the pot. Molten aluminium. The aluminium melt is periodically siphoned off from the bottom of the pots using a tapping track and transferred into a ladle. The casting process. Once the aluminium has been smelted, it is cast into different forms such as rolling ingots or extrusion billets. The casting process involves several stages. Grain refining. As the molten aluminium is transferred from the furnace, grain refiners are added. These can be in the form of a wire that dissolves into the melt to improve the metal's properties. Degassing. Argon gas is bubbled through the molten aluminium to reduce its hydrogen content, ensuring the metal's quality. Filtering. The melt then passes through a ceramic foam filter to remove any remaining impurities before it flows into the casting table. Mold filling and solidification. The molten aluminium is poured into molds on the casting table. A water-cooled shield helps in the initial solidification process, which ensures that the ingots form correctly as the mold is lowered. Air slip technique. This technique involves pressing air through a porous graphite ring, creating a film that prevents the molten metal from sticking to the mold, facilitating a smoother casting process. Post-casting treatment. Homogenization. The cast billets undergo heat treatment in a large furnace at around 518 degrees Celsius for about 3 to 4 hours to ensure uniform properties throughout the billet. This is the world's fastest band saw dedicated to sawing of aluminium billets manufactured by SERMAS industry. Compliant to 4.0 industry, the billet saws are able to cut a 12 inches O billet within 11 seconds. In-feed speed of the blade is 1/8 inch sec, 2 meters per minute, typical raw 5 to 10 micrometers. Reduced cut kerf to save large volume of chips. Full automated line integrating manipulators, marking system, stacking and strapping station, measuring device, etc. Here's an in-depth look at how FlowForm wheels are manufactured. Casting process. The process begins with a 356.2 aluminum alloy, selected for its strength and casting properties. This raw material is melted at approximately 1,400 degrees Fahrenheit, filtered, degassed, and inspected. Depending on the mold size, 50 to 100 pounds of molten aluminum at over 1,300 degrees Fahrenheit is poured into a steel mold, where the wheel's face is positioned at the bottom for stronger smoke formation. Once the casting solidifies, it is quenched in 120 degrees Fahrenheit water, trimmed and measured to confirm correct dimensions. The initial casting features a thick skirt that will be later flow formed into the final rim shape, enhancing the crystalline structure and strength of the wheel. Flow forming. Preheated castings are loaded onto a conveyor leading to a flow forming machine. Each casting is placed on a preheated mandrel, and rollers gradually squeeze the aluminum skirt into the final rim barrel shape. Multiple passes of the rollers ensure the material is properly shaped and strengthened. The wheels are then quenched again to maintain mechanical properties and reduce distortion. Heat treatment. After flow forming, the wheels undergo heat treatment to refine and align the aluminum structure, locking in the desired hardness. This involves heating the castings and quickly quenching them, further enhancing the wheel's strength and durability. Once the initial casting and flow forming processes are complete, each wheel undergoes an X-ray inspection. This non-destructive testing method ensures that there are no internal voids, cracks, or other imperfections that could compromise the wheel's structural integrity. After passing the X-ray inspection, the wheels proceed to the laving process. During this stage, excess material from the casting process is precisely removed to shape the wheel's final rim profile. Laving ensures that the wheel's dimensions and surface finish meet exact specifications. This step also involves creating the initial geometry of the rim, preparing it for further detailed machining. Detailed machining following the laving process, the wheels undergo detailed machining to create critical features necessary for vehicle compatibility. After machining, the wheels are subjected to concentricity and balance checks. Concentricity ensures that all circular features, such as the hub bore and rim, share a common center, preventing vibrations during driving. Balance checks involve spinning the wheel to detect any weight imbalances. Any necessary adjustments are made to ensure that the wheel is perfectly balanced, providing a smooth and stable ride. Finishing cleaning process. Before applying any finishes, the wheels undergo a thorough cleaning process. This step removes all manufacturing debris, machining residues, and any contaminants that could affect the adhesion of subsequent coatings. The wheels are loaded onto a hanging line and moved through a series of cleaning stations, where they are cleaned using specialized solutions and techniques. Powder coating. The first layer of finish is the standard black powder coat, known as tarmac. Powder coating involves applying a fine plastic powder to the wheel using an electrostatic charge. This charge ensures that the powder adheres evenly to all surfaces. The coated wheels are then heated in an oven, where the powder melts and cures into a hard, durable shell. This layer provides excellent protection against scratches, corrosion, and environmental factors. Clear coating. Following the powder coat, a liquid clear coat is applied. This coat is sprayed onto the wheels, providing a satin sheen that enhances the appearance and adds an additional layer of protection. The clear coat is also cured, ensuring it bonds securely to the powder coat. Special finishes. For finishes like liquid metal, a more complex, hand-sprayed technique is used. This process starts with a base layer of black paint applied over the entire wheel. A liquid silver paint is then carefully sprayed over the wheel's face, creating a dynamic, two-tone effect with depth and visual interest. This technique requires skilled operators to achieve the desired look consistently. Final quality checks. After finishing, the wheels undergo a series of final quality control checks. These include visual inspection, ensuring the color and finish quality meet HRE standards. Run-out test, verifying the wheel's roundness and ensuring it meets concentricity and balance requirements. Leak test, simulating tire pressure conditions to ensure the wheel can maintain air pressure without leaks. Once the wheels pass these stringent quality checks, they are considered complete. Packaging and distribution. Once the wheels pass all tests, they undergo additional QC steps, including center cap fitment, size, offset, and finish inspection. Approved wheels are boxed and shipped to HRE's warehouse in San Diego for final inspection before being distributed to dealers for tire mounting and vehicle installation. In this video, we will explore the most modern extrusion lines in Europe, high-speed bandsaw and production process of aluminum thin sheet coils. We are in Kaiser Aluminium's aluminum plant. Kaiser Aluminium is an American aluminum producer, headquartered in Franklin, Tennessee. In 2020, it recorded revenues of roughly $1.173 billion United States dollars. Kaiser currently owns 13 fabricating plants that can produce more than 400 million pounds, 180,000 long tons, of aluminum annually. The North American plants produce approximately 500 million pounds, 220,000 long tons, per year of value-added sheet, can sheet, plate, extrusions, forgings, rod, bar, and tube. In April 2021, Kaiser Aluminium completed acquisition of Alcoa Warwick LLC, renaming it Kaiser Warwick LLC. Presently, Kaiser Aluminium Warwick operates a cast house, hot mill, cold mills, finishing mills, coating lines, and slitter lines, producing flat-rolled aluminum sheet for the food and beverage container market. This is full automated slicing saw for aluminum plate production manufactured by SERMAS Industry. Full automated process to produce plates from cast slab, including associated handling equipment as well as many high technology solutions to brush to remove chips from the plate after sawing, weighing system, vacuum handling manipulator, paint marking system, and automatic labeling device for cut product up to the compacting press to evaluate chips. SERMAS Industry is a global leader in the sawing of large dimensions materials for the aluminium and non-ferrous industries. They design, manufacture and start up complete sawing plants for aluminium and non-ferrous materials. They also design and produce equipment to process anodes and cathodes, sealing bench, matting station and specific handling solutions. Aluminum shell casting, specifically gravity casting, is a pivotal process in this aluminum foundry. This method involves pouring molten aluminum into a mold using gravity, allowing the metal to naturally fill the cavity. This technique is celebrated for its ability to produce high-quality, dimensionally accurate components with a fine surface finish. The investment in advanced technologies has significantly enhanced the production capabilities and quality assurance. One of the major upgrades is the automatic casting plant, which features 2 anthropomorphous robots. These robots streamline the casting process by automating tasks such as mold handling and pouring, which not only boosts efficiency and consistency but also enhances workplace safety by minimizing human interaction with molten metal. Another key innovation in the foundry is the computerized burr machine. This equipment automates the removal of burrs and other imperfections from the cast parts, ensuring a smooth finish and reducing the need for manual labor. This not only improves the overall quality of the cast components but also represents a significant advantage for occupational safety, as it reduces the potential for injuries associated with manual deburring processes. In addition to the technological advancements, the foundry prioritizes close collaboration with our customers during the mold design phase. Utilizing sophisticated 3D design software, they work together with clients to create precise mold designs. Quality assurance is at the core of the operations, supported by the Comprehensive Analysis Lab. Equipped with a spectrometer, X-ray machine, density scale, and traction machine, the lab performs rigorous testing on alloys and cast products. The spectrometer analyzes the chemical composition of the alloys, ensuring they meet required specifications. The X-ray machine inspects the internal structure of the cast parts for any hidden defects. The density scale measures the density of the alloys, which is crucial for ensuring material consistency. Finally, the traction machine tests the mechanical endurance of the alloys, guaranteeing the durability of products. The mechanical machining department of the workshop excels in precision mechanics, known for its exceptional flexibility and dynamism in meeting customer requirements. Emphasizing speed and precision, the department leverages cutting-edge technical capabilities developed through continuous research and innovation. The facility is equipped with the latest generation of 4.0 technology machinery, enabling real-time monitoring of each machining process. Advanced equipment includes multi-pallet CNC machining centers and lathes, enhancing the ability to perform intricate turning and milling operations. These CNC machine tools feature 2, 3, 4, and 5 axes, allowing for complex and precise machining tasks. The manufacturing process of pressure cookers at Landers starts with material selection, where aluminum is chosen for its lightweight, corrosion resistance, and excellent thermal conductivity. Engineers design the pressure cookers, considering safety, efficiency, and user convenience. Prototypes are made and tested for functionality and durability. Large aluminum sheets are cut and shaped into the body of the pressure cookers using high-precision machinery, while parts like handles and bases may be created using extrusion or casting processes to ensure strength and stability. In the welding and assembly stage, different parts of the pressure cooker, including the base, handles, and lids, are welded or assembled using screws and rivets. Special attention is given to the lid and its locking mechanism to ensure a secure seal. Pressure valves, safety plugs, and gaskets are installed next, as these components are critical for maintaining the correct pressure and ensuring user safety. Each pressure cooker undergoes rigorous testing to withstand high pressure and to ensure that the safety mechanisms function correctly. Once assembled, the pressure cookers are polished to remove any imperfections and may be coated to enhance appearance and provide additional corrosion resistance. Detailed inspections are conducted to ensure that the pressure cookers meet stringent quality standards. Finally, the finished products are packaged with user manuals and warranty cards, with packaging designed to protect the cookers during transportation. Landers pressure cookers are designed for longevity, with a 10-year warranty indicating their durability. Proper maintenance is crucial for ensuring these cookers last a long time. After each use, the pot should be cleaned thoroughly, with special attention given to the ring and the valve to prevent clogging and ensure the seal remains intact. Regular inspection of the gasket, valve, and other parts for wear and tear is important, and replacements should be made as needed to maintain safety and efficiency. Users should avoid overfilling the pressure cooker, maximum 3/4 full, and ensure it is used as per the manufacturer's guidelines. Initially, the production at here included pressure cookers in sizes of 4 and 6 liters. Over the years, the company expanded its product line focusing primarily on aluminum pressure cookers due to its durability and excellent heat conduction properties. We are in the plant that has one of the most modern extrusion lines in Europe. It is the new 8.5 extrusion line of Indinvest LT in Cisterna di Latina, near Rome, for which OMAV is supplying all the equipment ahead of and behind the extrusion press, including the rack handling system. A number of new and further developed features will be used. Indinvest LT is an extrusion plant known beyond the frontiers of Italy, which produces mainly industrial profiles and extrusions for windows and doors. Today, the company has 4 presses, 5, 7, 8.5 and 10-inch, and a billet casting plant with an output of almost 60,000 tons per year. The factory is providing high-end clients who demand services, quality and additional processing, also paying great attention for foreign markets. Today, Indinvest produces approximately 50,000 tons per year of extruded profiles with 20,000 different section types. Micro profiles from 25 grams per meter up to those weighing more than 20 kilograms per meter. With the new extrusion equipment, the production capacity will amount to 60,000 tons. In fact, to increase its capacity, the company has ordered another extrusion line from OMAV. Directly at the runout, the furnace is connected to a hot shear. Which cuts up the hot logs into individual extrusion billets. In contrast to conventional hot shears, with which the ends of the billets are usually inadvertently deformed, the OMAV shear has movable blades that produce a largely straight cut. Thanks to this, the deformation at the billet ends is so well suppressed that two short billets, one behind the other, can be placed closely against one another in the extrusion press and extruded without problems. In combination with the use of the optimization software developed by OMAV, this gives an appreciable output improvement. The entire runout system behind the press is designed for double lengths. The length of the extruded profiles is 62 meters. The profiles are drawn out by double pullers, which are also a new feature of OMAV's product range. The puller tracks extend laterally, with one puller running on the floor and the second suspended on a rail above. The pulling force of the pullers is 150 kilograms. Aluminum sand casting is a widely used method in the manufacturing industry, known for its versatility and cost-effectiveness. When producing components such as aluminum alloy wheels, sand casting offers several benefits, especially when combined with carbon dioxide, CO2, molding techniques. This process, however, comes with its own set of advantages and disadvantages that are crucial for manufacturers to consider. Sand casting involves creating a mold from a mixture of sand and a binder, which can withstand the high temperatures required to melt and cast aluminum alloys. The process includes creating a pattern of the desired wheel, forming a mold cavity by packing the sand around the pattern, and then pouring molten aluminum into the cavity. Once the aluminum solidifies, the sand mold is broken away, revealing the cast aluminum wheel. Carbon dioxide molding process. In carbon dioxide molding, sodium silicate, water glass, is used as the binder for the sand. After the sand mixture is shaped around the pattern, it is exposed to CO2 gas, which reacts with the sodium silicate to harden the mold almost instantaneously. This results in a rigid and durable mold suitable for high-precision casting. Advantages of carbon dioxide molding in aluminum alloy wheel sand casting. Precision and surface finish. The CO2 molding process provides excellent dimensional accuracy and surface finish. The hardened molds maintain their shape well, reducing the need for extensive post-casting machining. This is crucial for aluminum alloy wheels, where precision impacts performance and aesthetics. Strength and durability. CO2 hardened molds exhibit superior strength and durability, which is beneficial for casting intricate designs and thin sections of aluminum alloy wheels. The increased mold rigidity helps prevent deformation during the casting process. Shorter cycle times. The rapid hardening of molds in the CO2 process leads to shorter cycle times compared to traditional sand casting methods. This efficiency can result in higher production rates, which is advantageous for meeting high demand in the automotive industry. Cost-effective. While the initial setup for CO2 molding may be slightly higher, the overall cost savings from reduced machining, less mold maintenance, and higher production rates make it economically viable. Additionally, the sand used in CO2 molding can often be reclaimed and reused, further reducing material costs. Environmentally friendly. The CO2 process involves less use of chemical binders compared to other methods, leading to lower emissions and a smaller environmental footprint. The reusability of sand also contributes to a more sustainable manufacturing process. Disadvantages of carbon dioxide molding in aluminum alloy wheel sand casting. Complexity in mold making. The CO2 molding process requires precise control of gas application to ensure uniform hardening. Any inconsistencies can lead to defects in the mold and, consequently, the cast product. This necessitates skilled labor and careful monitoring, increasing the complexity of the process. Initial equipment cost. The setup cost for CO2 molding equipment, including gas application systems and safety measures for handling CO2, can be higher compared to traditional sand casting methods. This initial investment may be a barrier for smaller manufacturers. Limited mold flexibility. Once hardened, CO2 molds are less flexible and more brittle than traditional green sand molds. This brittleness can result in mold breakage during handling or casting, especially for intricate or delicate designs. This can lead to increased scrap rates and potential production delays. Health and safety concerns. The use of CO2 gas requires stringent safety protocols to prevent accidents, such as CO2 exposure or asphyxiation risks in poorly ventilated areas. Proper training and safety equipment are essential to mitigate these risks, adding to the operational costs. Moisture sensitivity. Sodium silicate molds are sensitive to moisture, which can cause premature hardening or degradation of the mold. This requires careful control of the working environment and storage conditions for the sand and molds, potentially complicating the manufacturing process. Aluminum spinning, a versatile metal forming process, has a rich history and significant applications in various industries. In Mexico, the art of creating a 120-liter steamer through aluminum spinning is a testament to the country's blend of traditional craftsmanship and modern engineering. This process not only showcases the technical prowess of Mexican artisans but also highlights the cultural significance of metalworking in the region. The aluminum spinning process. Aluminum spinning is a metalworking technique where a metal disc or tube is rotated at high speed and formed into an axially symmetric part using a lathe and various shaping tools. This method is favored for producing seamless, round, and conical shapes, making it ideal for crafting large steamers. Material selection. The journey begins with selecting the appropriate aluminum alloy. For a steamer, the alloy must possess excellent corrosion resistance, thermal conductivity, and strength. Common choices include 1100, 3003, and 5052 aluminum alloys, each offering a balance of these properties. The aluminum sheet is usually procured in large coils or plates, which are then cut into circular blanks. Tooling and equipment. The spinning lathe is the heart of the process. This lathe must be robust enough to handle the large aluminum blank required for a 120-liter steamer. The lathe includes a rotating mandrel, which serves as the mold around which the metal is formed, and various roller tools that shape the aluminum as it spins. Forming the steamer. Mounting the blank. The aluminum blank is secured onto the spinning lathe's mandrel. For a steamer, the blank size is substantial, necessitating precise alignment to ensure symmetry. Spinning. The lathe spins at high speed, typically between 500 to 2000 RPM. As the blank rotates, the operator uses roller tools to apply pressure, gradually forcing the aluminum against the mandrel. This process requires skilled hands, as the pressure must be applied evenly to avoid imperfections. Intermediate annealing. During spinning, the aluminum workpiece may undergo intermediate annealing, a heat treatment process that softens the metal. This step is crucial for maintaining ductility and preventing cracking, especially given the large size and complex shape of the steamer. Final shaping. The operator continues to work the metal until it conforms precisely to the shape of the mandrel. For a steamer, this involves creating a wide, cylindrical body with a flared rim. Attention to detail is critical to ensure uniform wall thickness and a smooth surface. Additional fabrication steps. Once the primary shape of the steamer is achieved, several additional steps are undertaken to complete the manufacturing process. Trimming and smoothing. The edges of the spun steamer are trimmed to remove excess material and ensure a smooth, even rim. This is typically done using cutting tools on the lathe. The surface may also be polished to enhance its appearance and remove any minor surface imperfections resulting from the spinning process. Forming handles and lids. Steamers often require additional components such as handles and lids. Handles are typically fabricated separately, either through casting or forging, and then welded or riveted onto the body of the steamer. The lid is usually spun in a similar fashion to the main body, ensuring a perfect fit. The lid might include a knob or handle, which is attached using rivets or screws. Assembly and finishing. The final assembly involves attaching any additional components and conducting a thorough inspection to ensure quality. The steamer is checked for structural integrity, uniformity in thickness, and the smoothness of its surface. Any necessary adjustments or refinements are made at this stage. Quality control and testing. Quality control is an integral part of the manufacturing process. Each steamer undergoes rigorous testing to ensure it meets the required standards. This includes dimensional accuracy, ensuring that the steamer's dimensions conform to design specifications. Leak testing. Checking for any potential leaks, especially around welded or riveted joints. Load testing. Verifying that the handles and overall structure can withstand the weight of a full steamer. Cultural and economic impact. The production of large aluminum steamers in Mexico is not only a technical endeavor but also a cultural one. Metalworking has deep roots in Mexican history, dating back to pre-Hispanic times when indigenous peoples crafted metal artifacts. Today, this heritage is preserved and evolved through modern manufacturing techniques like aluminum spinning. Economically, the production of aluminum steamers supports local industries and artisans. It creates jobs, fosters skill development, and contributes to the local economy. Mexican-made aluminum steamers are also exported, showcasing the country's craftsmanship on a global stage. The production process of aluminum speaker baskets begins with the selection of high-quality alloy aluminum ingots. The quality alloy aluminum ingots are melted in specialized furnaces. These furnaces are designed to achieve the precise temperatures required to melt aluminum without compromising its inherent properties. Once the aluminum is in its molten state, it is transferred to a talpress injectors. These high-precision injection machines are critical in shaping the molten aluminum into the desired speaker basket forms. The Italpress injectors ensure that the aluminum is injected into the molds with the utmost accuracy, guaranteeing uniformity and quality in each piece produced. Roughing. Removal of excess and handling. After the aluminum has been injected and formed, the roughing stage begins. This involves the removal of any excess material from the cast pieces. The initial handling and roughing are crucial to prepare the pieces for further refinement, ensuring that they are free from any major imperfections or excess material that could affect the final quality. These panels allow for precise control over the injection parameters, including pressure, temperature, and injection speed. Following the roughing process, the speaker baskets are trimmed using cutting presses. This step involves the fine removal of any remaining excess material and the precise shaping of the baskets. The cutting presses ensure that each piece is trimmed to exact specifications, maintaining the integrity and design required for optimal performance. Shot blasting machine. The nearly finished speaker baskets are then subjected to shot blasting. This process involves bombarding the baskets with small abrasive particles to smooth the surface and remove any minor imperfections. Shot blasting not only enhances the aesthetic appeal of the baskets but also prepares the surface for any subsequent finishing processes, such as painting or coating.